Alright, so we're going to look at the equations of planes now. So lecture 28, there's a lot of prior knowledge up to this point, so I'll put all these links below, but definitely go and watch these if you haven't already. So we looked at introducing what vectors are, resolving vectors into rectangular components, the dot product between vectors, collinearity, vector equations of lines, intersections and skew lines, and the cross product. Going to need to draw on all of this information in order to define the equation of a plane in space. So the concepts we'll cover here are normal vectors to planes, the equation of a plane, finding the equation of a plane when you get given a point in a normal vector, when you get given 3 points, and when you get given 2 intersecting lines. So sort of big idea stuff here. If we just sort of look at this sort of image, a plane is sort of like a sheet of paper situated some way in space, right? So this is sort of a artistic way of looking at that. But let's jump into it. Let's have a look at normal vectors to planes. So again, a plane is this sort of sheet of paper situated in space. A normal vector is a vector that is at right angles to that plane. So you can see here we've got this sort of, in blue we've got our plane, and then you can see coming off that plane we've got all these normal vectors. Now these are just randomly placed. And we can say that a normal vector to a plane is perpendicular to it. A plane has infinitely many normal vectors, because what we can do is we can scale up or scale down our vector, our normal vector n, by some scalar k. So you notice if I change this k value, I can change the size of those vectors, and they're all normal vectors because they're all perpendicular, but some of them have different sizes, right? So we end up with this situation. When k is negative, we obviously get it pointing in the opposite direction. Yeah, so finding the normal vector. So given some plane equation, ax plus by plus cz equals d. Okay, a, b, c, and d are all sort of real number sort of coefficients. And if we set up some equation like that, we know that a normal vector is given by just the coefficients of a, b, and c. And I should maybe be a little bit clearer. Another way we could represent that normal vector n would be capital A multiplied by the unit vector I plus capital B multiplied by the unit vector j plus capital C multiplied by the unit vector k. That's sort of just another notation here. Let me fix that up so it makes more sense. Yeah, so just making that a little bit clearer, because this is not really a notation we've used before, but we can say that the normal vector is equal to capital AI plus B multiplied by J plus C multiplied by K. This can sometimes just be a shorthand, because we're just talking about that point. So this would just be a position vector pointing at this point here, which is at 2, 1, negative 1. I encourage you to think about why the coefficients of a plane equation give you a perpendicular vector to that plane, and I would encourage you to think in 2 dimensions before you start to think in 3 dimensions. I've made a video about that elsewhere, and I'll try and find that and put a link below. But what you need to know for now is that, yeah, to get normal vectors to a plane, it's just perpendicular to some plane in space. And yeah, one of the ways that you can come up with a normal vector is to take the coefficients and turn that into a vector. So let's have a look at the next thing. So we're looking at the equation of a plane now. So that was just talking about normal vectors. Now looking at the equation of a plane. So a plane, pi, this is capital pi in Greek, is defined using 2 vectors. So you need a position vector A of a point on the plane and a normal vector n perpendicular to the plane. Let's just pause there and think about that for a moment. Again, we've got this plane here in space. Let's just look at key features here. Let's imagine we've got some vector A that's pointing at some point here. This point here is the point A. And so we've got this position vector, A, pointing at this point here, capital A. And once we know that point, as long as we know a normal vector to the plane, which you can see over here we have as n, we can see that that's at right angles to the plane, then that's all you need to define the entire plane in space, because that one point, A, fixes it, and then if you know a normal vector to that point, then you know all the points that would also be perpendicular would have to sit on that same plane. So the key information we need in order to define the equation of a plane is a position vector of a position vector of a point on the plane, and a normal vector to a point on the plane. So we can also say for any point P with position vectors r minus a dot n equals 0. Okay, this is where it gets a bit confusing, but let's have a look. Let's see if we can make some sense. You'll notice here we've got the point A. Let's pick some other random point P, which we're just going to put on the plane over here. Using a bit of vector subtraction, I think you would agree that r minus a would be this vector going from A to P, because doing vector subtraction, you would agree that this is the same thing as negative a plus r. So it'd be traveling this way plus this way. This vector has been reversed, and then we're adding this, so the vector r minus a does in fact go from here to here. And we know that that vector r minus a is also on the plane, and so we know that it has to be perpendicular to that vector n. So what we know that the plane must satisfy this equation. R minus a multiplied by n, shouldn't say multiplied, the dot product between r minus a and n is equal to 0, because we know that the dot product between two perpendicular vectors is equal to 0. Okay, we also know that the dot product is distributive. So if we distribute that n in, we get r dotted with n minus a dotted with n. Bring the a dot n to the other side, and you'll see that the vector equation of this entire plane is r dot n equaling a dot n. Okay, and let's just really drill down into what these things are. So r is r is the vector that defines the plane. So it's got coordinates x, y, and z. So the vector r is equal to xi plus yj plus zk, and n is our normal vector, which has the coefficients n1, n2, and n3. Right, so that's sort of talking in general terms there. If we then wanted the Cartesian equation, well, what we would do is we would just take the dot product between these two things. So r dotted with n, so you take the dot product between this and this. So that'd be n1x plus n2y plus n3z, and that equals some constant k, and k is equal to the constant a dotted with n. Remember, a and n are known. Okay, we know what vector a and vector n are, because it's the minimum information we need to define the plane in space, and so then we call that some constant k. I think an example will make more sense. So the example says this: let's imagine we've got a normal vector, which is 2i plus 3j minus k, and we have a point that's on the plane, I plus 2j plus 3k. So what we can sort of say to ourselves at the moment, if we sort of think of this example, this point here, A, is at the point 1, 2, 3. It's not actually, but just for argument's sake. And then the normal vector, so this vector that's sort of here, perpendicular to the plane, is 2i plus 3j minus k. Okay, and we know if we want to find the equation of the plane, it has to satisfy this condition. Okay, because we know r minus a has to also be on that plane. So we get r minus a dotted with n equals 0. Okay, and then we expand that. Okay, when we take vector r minus vector a, we just do the subtraction of their coefficients. The coefficient of the I component of r is x. The coefficient of the I component of a is 1. So this first part becomes x minus 1. Plus y minus 2 plus z minus 3. And then we're going to take the dot product with that with the normal vector, which is 2i plus 3j minus k. And we know that that has to equal 0. And remember, the dot product gives us a number as the answer. So we get x minus 1 multiplied by 2 plus y minus 2 multiplied by 3 plus z minus 3 multiplied by negative 1. That all has to equal 0. And then you simplify that and you get 2x plus 3y minus z equals 5. And so that's what this blue surface is, right? This plane is defined using this Cartesian equation, 2x plus 3y minus z. And it's a bit tricky to explain, but you know, if you think in 2 dimensions, if you think y equals 2x plus 1, the line that would sketch out is all the points that would satisfy that equation, right? Similarly, in 3 dimensions, we've got an extra variable, but this plane is all the points that satisfy this equation, all the x, y, and z points that would satisfy this equation here. So that's how you define the equation of a plane in 3-dimensional space. Okay? Hopefully making some sense. Let's have a look at the next thing. Okay, so now we're just going to look at some examples, and the first example is finding the plane determined by a point and a normal vector. So let's imagine a plane is such that the vector 2i minus 3j plus k is normal to the plane, and the point A with position vector 4i minus j plus 5 is on the plane. So that's that point here, and this is the normal vector pointing out of that plane. Now, our job is to find a vector equation of find a vector equation and a Cartesian equation of the plane. Okay, so what we need to do is we need to use the form that we just spoke about. So we know that for a plane, it needs to satisfy this kind of equation. The dot product between r and n is equal to the dot product between a and n. Okay, remember a is a position vector and n is a normal vector to the plane. Okay, we know that n is 2i minus 3j plus k, and we know that r just has coefficients of ij and k of x, y, and z respectively. So yeah, in the vector equation form would be this: r dotted with 2i minus 3j plus k equals 4i minus j plus 5k, which is the position vector, dotted with 2i minus 3j plus k, which again is the normal vector. Okay, taking the dot product between these, we know that the dot product of this part is 4 times 2, which is 8. Negative 1 times negative 3 is 3. 5 times 1 is 5. So we know that the right-hand side is equal to 16. And the left-hand side just remains as this vector r dotted with 2i minus 3j plus k. So that's it in the vector equation form of this plane. Now the Cartesian equation of the plane is that we know that this vector r is just xi plus yj plus zk, and then so we just take the dot product between that. So we know that r is just this, so just substituting that in. So it's 2x minus 3y plus z equals 16, and that is this plane here in space, right? So that's how we find the plane determined by a point and a normal vector. So you're given a point, you're given a normal vector, and you can find the vector equation and the Cartesian equation. Okay. Now let's look if you need to find the plane when you get given 3 points. So 3 points is enough to determine the position of a plane, provided they're not collinear. And again, we've spoken about collinearity before, so definitely go have a look at that with some of the links below. Just again making an analogy with sort of linear relations, in 2 dimensions, the minimum number of points you need to define a line is 2, but in 3 dimensions, the minimum number of points you need to define a plane is 3, as long as they're not collinear, as long as they're not just all in a straight line, basically, because then you don't define a plane. So let's look at the kind of problems you might be asked. So consider the plane containing the points 1, 2, 0, 3, negative 1, 1, and negative 2, 0, 4. Find a Cartesian equation of the plane. Okay, so let's just get a visual picture of what's going on. So this point here is A, so that's at 1, 2, 0. This point here is at B, so that's at 3, negative 1, 1. And this last point here is at C, which is negative 2, 0, 4. Okay, what we're going to need to do to find the Cartesian equation of the plane is we're going to need the vectors AB and AC. So let's put those in. So that's a vector there from A to B is vector AB, and from A to C is vector AC. So you can see already that these points would sort of create a plane, right? We could draw a plane in there, and we'll do that in a moment. But you can certainly see if we get the angle right that these all sit sort of on some sort of plane, right? Okay, but remember from before, what would be nice in terms of defining our plane equation would be to know the normal vector. So if we know the normal vector, or a normal vector, then we can sort of get the orientation of the plane, right? And this is where we're going to use the cross product. Okay, so before we do that, we just need to define vectors AB and AC. Okay, remember the vector A to B, that's going to be a vector subtraction, okay? Because imagine vectors going from the origin to A and then from the origin to B. If you did a vector subtraction, it would be vector B minus A, or vector AB. Yeah, I'm not explaining that very well, but just imagine that there was a vector from the origin to A and from the origin to B. Vector B minus vector A would give you the vector AB. In any case, hopefully you can see where this comes from. So you would take 3 minus 1 I, minus 1 minus 2 j, 1 minus 0 k. So we know that the vector AB is 2i minus 3j plus k. That's this vector here. Okay, similarly we do the same thing with AC. AC is minus 3i minus 2j plus 4k. Alright, now's the more important part where we need to take the cross product between them. Because remember, the cross product gives us a vector that's perpendicular to those two vectors, yeah, from previous videos. So the vector product, or the cross product of AB cross AC is this. We basically need to define the determinant of this matrix. I trust that you can crunch the numbers. This is the process you need to follow. You'll get this negative 10i minus 11j minus 13k, and that's a big vector pointing in that direction. But if I get the angle right, you can hopefully see that that's at right angles. This vector here is at right angles to the plane containing points A, B, and C, right? So we end up with a situation like that. Okay, therefore the vector n, the normal vector is negative 10i minus 11j minus 13k is normal to the plane. So using the point A, 1, 2, 0, and the normal n, just like we did before, once you've got the normal vector and a point on the plane, you can determine the Cartesian equation just like we did before. And it turns out that this is your answer. Negative 10x minus 11y minus 13z equals negative 32 is the plane that will contain A, B, and C. And I can actually show you that if I click on C, A, and B, that's that plane there. So if this last step seems a little bit confusing, it's just follow the steps we did in the previous section. That's how we came up with that. Okay, so yeah, that is the plane equation when you are given 3 points. Okay, last one. We've got to find the plane equation when you get given 2 intersecting lines. So let's look at this example. So 2 lines that intersect at a single point can be used to determine a plane. Okay, so that should hopefully make some sense. Let's maybe get a picture in our heads of what's going on. We've got this plane here. We've got these 2 vectors, pink and orange, that define lines in space. So let me just show you those lines. If we just trace these lines out, there's one line. You could obviously imagine it's fully filled in, and there's the other line. It's the sort of situation we're dealing with. I think you would agree, as long as those lines intersect, there's going to be a plane, aka this blue plane, that will contain both of those lines, right? If they're skew lines, remember skew lines are not parallel and they don't intersect, then there won't be a plane that contains both lines, right? But if the two lines do intersect, there will be a plane. Okay, so what we want to do is find a vector equation and a Cartesian equation of a plane containing the lines, these 2 lines, 5i plus 2j plus lambda multiplied by 2i plus j plus k. Okay, and this is line 2, right? Okay, the solution, we know that a point on the plane must be 5i plus 2j, because we know that this is sort of the position part, or this is a point on the first line, right? Remember, this part gives us the gradient, this part defines a point on the line when lambda is 0. So if lambda goes to 0, this whole thing disappears, and we know that 5i plus 2j must sit on the first line. Okay, and we want to find a normal vector, so it must be perpendicular to both. Okay, so let's look at the position vectors. The position vector of, the direction vector of line 1 is 2i plus j plus k, and of line 2 is I minus j minus 2k. Okay, we need our normal vector to be perpendicular to both of those lines. So again, we need to take the cross product, because if we take the cross product, we will get a normal vector to both of those lines, or both of those vectors that determine those lines, I think would be better to say. Okay, so you get this, you again compute the determinant of this matrix, negative I minus 5j minus 3k, so we know that n is negative I minus... One sec. Sorry, there was a very small error here with this 5. Anyway, we get that the normal vector is negative I plus 5j minus 3k. Okay, we know that the point A is on there. And we know that the plane equation, the vector equation of the plane, is r dotted with n equaling a dotted with n. And so we get this. This is our plane equation, r dotted with negative I plus 5j minus 3k equals 5i plus 2j dotted with the normal vector again. Simplifying, we get r dotted with negative I plus 5j minus 3k. The dot product of the right hand side turns out to be 5. And so this is our vector equation of the plane. R dotted with negative I plus 5j minus 3k equals 5. And sure enough, following the steps from 2 or 3 slides ago now, the corresponding Cartesian equation is negative x plus 5y minus 3z equals 5. And that should be reasonably obvious just looking at that. And yeah, so that is they're the Cartesian and vector equations of this blue plane in space. 2 different ways to define it. There is also another way to do it using parameters, but I'll leave that as an exercise for you to go and do. Yeah, hopefully you found that useful. Again, it's a bit hard to explain some of these things, probably easier just to pause the video and read it. But it is what it is. So good luck. Let me know if you need any private tutoring, and I'll talk to you soon.